Welcome to ITC Lunch. Today we're going to start with Diana Powell, one of our Sagan Fellows and I think ITC Fellow? Or only Sagan Fellow? Anyway, she is often seen in the ITC hallway, so we'll claim her. So Diana, please.
Yeah, hello, and thank you so much for having me. So yes, I'm Diana Powell, and I'm a Sagan Fellow, but at the ITC. And today I'm really excited to talk with you all about the depletion of gaseous CO in protoplanetary disks. And particularly, I'll be focusing on the effects of surface energy regulated ice formation. Okay. So before I jump into the details of protoplanetary disk compositions, let's briefly touch base on the general picture of planet formation that has emerged. So planets form in protoplanetary disks, either from the accretion of gas and solids or the gravitational collapse of material. So protoplanetary disks are the building blocks of planet formation. Then once the bulk of the protoplanetary disk dissipates, a young planetary system remains, and if there are gas giants present, they'll be initially relatively hot. And then as time evolves, the planetary system will evolve, the gas giants, if they're present, will cool, and the planetary atmospheres will evolve. Okay, so this is the general picture. But what I really want to know is how do we relate these disparate evolutionary stages to learn about the full complement of planetary formation and evolution? So for the full complement of planetary systems. And the way that I approach understanding relating these disparate evolutionary stages is from the perspective of chemical compositions using microphysics. And if you ever hear me refer to microphysics, I'm particularly referring to the evolution, or the physics that governs the evolution of small particles, often in the presence of gas. So for the purposes of this talk, I'm really talking about small ice or dust particles. Okay, so with this understanding, let's focus on the question of the composition of protoplanetary disks, which is really fundamental for our understanding of planet formation and evolution. So in particular, the radial and temporal composition of both the gaseous and solid components in disks directly influences the composition and properties of the planets that form. So thus, understanding disk compositions not only tells us things about planet formation, but also gives us this novel lens to view planetary atmospheres, bulk compositions, and planetary evolution processes. And happily for us, we can now observe the gaseous composition of protoplanetary disks in unprecedented detail. So here I'm showing the MAPS ALMA survey of several molecular lines towards 5 diverse, bright protoplanetary disks. But despite this level of detail, these observations still do not immediately reveal to us the detailed compositional properties of the solid and gaseous components in the planet-forming regions of the disk. And this is what we really need to know for detailed comparisons across evolutionary time. And this is because determining the compositions of disks that are directly relevant for planet formation is difficult. And to get an idea of why this is the case, let's take a quick look at this vertical cross-section, or this cross-section of a disk here. So the planet's host star is on your right, and the disk flares out to larger radii on the left. And planets form in the disk midplane, which makes this a region of particular interest. However, in the midplane, the ice particles that are present are feeling some gas drag, which causes them to lose some angular momentum and drift inwards towards their host star. So this radial drift will alter the composition. And this radial motion may eventually cause ice particles to reach warmer regions of the disk where they release their volatile mantles, again altering the composition. And we expect some diffusion to be present in these systems that's causing the gas to mix around, altering the composition. And then not only are these systems in this constantly non-equilibrium state, but there's often enough gas present in the upper regions of the disk that it's optically thick, such that when we're looking at emission, we're observing the upper regions of the disk and not the midplane where planets form directly. Okay, and I should say this is all particularly true once we look at the inner regions of disks where we know that planet formation is common. So determining the midplane compositions of disks is difficult. And so while several molecules have now been observed in disks, the most commonly observed molecule is still gas phase CO, as it's relatively easy to observe. And difficulties relating to understanding the composition of disks is already evident in the observational literature, where several lines of evidence suggest that gas phase CO is depleted in disks, so particularly in the commonly observed upper disk layers. And so I'll just briefly touch on two such observations, but I'll note that there's now a large observational literature on this topic. So on the left here, I'm showing the CO abundance in the disk TW Hydra as a function of radius as compared to the average abundance we'd expect from the interstellar medium. So you can see that CO gas appears to be significantly depleted. And then the same appears to be true if we look at large samples of disks. So here I'm showing an ALMA survey of disks in Lupus, where on the top plot here, we're looking at the disks in dust mass, where we see that their dust masses span several orders of magnitude. But then if we look at their gas masses as estimated from CO, we see that they're roughly constant. And so in short, we observe much less CO in disks than we would expect, or than would be predicted using previous disk models. And to address this problem, I've coupled a model that I've developed for the aerodynamics of particles in disks, which can be used to make an inference about the total disk mass without an assumed tracer to H2 ratio. And I've added this to an adapted version of the models that I used to study cloud formation in exoplanet atmospheres. And in this context, I'm modeling the formation of ice on dust in disks, CO ice. And I'll start by pointing out that, in particular, the nucleation and condensation processes in this scheme include several effects of surface energy, so including the Kelvin effect, which quantifies the stability of particles through considering the strength of the molecular surface bonds. And so the strength of this effect depends on the species-specific material properties, but in a simplified sense, I like to think of this just in terms of geometry, where an ice molecule on the surface of a small grain won't be able to molecularly bond to as many neighbors as an ice molecule on a large grain. And so in short, when we consider the Kelvin effect, large particles nucleate and condense ice more easily than small particles. And so with the inclusion of the Kelvin effect, we derive particle size distributions in protoplanetary disks that are significantly different from the classically assumed case. So here I'm plotting the particle size distributions in terms of mass as a function of particle radius and height in the disk for a given disk semi-major axis. And so here the ice-free grains are in blue and the ice-coated grains are in green. And there's a lot of interesting detail in these plots that I'd love to talk about, but for now I'll just draw your attention to the fact that when we include the Kelvin effect, the ice is coated on the largest particles in the size distribution preferentially, while without that effect we see ice on particles of a diverse range of sizes. And the particle sizes are crucially important here because they regulate the level of depletion of gas phase CO. So if we approximate the disk vertical temperature structure at a given semi-major axis, as I'm doing here on the right, or the disk, or your left, where the disk is roughly isothermal until you reach a height in the disk where surface layer heating is efficient. If we're exterior to the midplane ice line, there'll be a region of the disk where ice is stable or ice can form, and then a region that is warm enough where evaporation or ice photodesorption may occur. So thus, if we have a small ice particle that forms in the midplane, it can be readily lofted to the regions of the disk, or it will release its volatile mantle back into the gas phase, such that CO gas will not be as easily depleted. However, if an ice particle is large, it can deplete the CO gas in the midplane, so it's not lofted as readily. And so that's what I'm showing here on the right. So if our initial abundance of CO gas, as shown in the solid black line, is depleted via ice formation as shown in gray, then due to diffusive mixing and a continued ice formation, we will eventually deplete the CO gas in the disk to what's shown here in the solid red line. So this is the so-called cold finger effect, which can lead to a large depletion of gas phase CO. But the particles and gas in the system evolve radially as well as vertically. So when we put this all together, at early times, gas is depleted fastest just exterior to the midplane CO ice line, where ice formation can happen, but also gas diffusion is relatively fast. Then, with time, CO gas is increasingly depleted in the outer disk as diffusion has more time to operate. And in the inner disk, ice particles drift inwards where they release their CO material into the gas phase. This causes there to be an enhanced abundance of CO gas in the inner disk that can then be accreted onto the host star in this enhanced abundance. And so with all of this in mind, let me quickly walk you through the evolution of CO in disks. So in the outer disk, CO gas is continually mixed towards the midplane, where ice formation occurs on large particles. These large particles drift inwards towards their host star until they reach a region of the disk, the midplane ice line, where they can cross the ice line and release their volatile material back to the gas phase, and then some interesting cycling of material occurs around this point. And then there will now be an enhanced abundance of CO gas in the inner disk that can be accreted onto the host star. And when we apply this modeling to observed systems, we find good agreement between our results and observations, as I'm showing in the small plots B through E here. And in our modeling, we find that this depends strongly on the bulk diffusive mixing characteristics of the disk. And so that contributes to the observed variance that we see in CO depletion between different systems. And so in the large plot here, you can see that the amount of observed depletion in the outer disk depends on the amount of diffusion that's operated in the lifetime of the system. And using this model, I can constrain the solid and gaseous CO inventory at the disk midplane where planets form. I can also constrain the bulk disk diffusivities and mixing characteristics, and resolve inconsistencies in disk mass that arise when you look at different tracers. So CO versus dust versus something like particle drift. And so these are three crucial parameters that control planetary formation. And all of this work is really just the beginning, because these processes are also applicable and crucial to other volatiles and disks. So the microphysical processes of ice formation both regulates the observed abundances of CO gas and determines the radial and temporal composition of disks. And so this is not just for CO, but for the other key volatiles, which are also in turn key planetary building blocks. So with future modeling along these lines, we'll be able to improve our understanding of the compositional initial condition of planet formation. Thank you so much.
Thank you. We have time for a few questions. People who know more about disks than I do. Arjun.
I definitely don't know anything about this. I was curious, given all the processing that happens in the disk, and you made the point at the end that the abundance of CO, for instance, could be higher in the part that's depleting onto the star. What is the relative ratios of carbon and oxygen and so on that are in the stellar atmosphere compared to around in the like the cloud, for instance, that starts out?
Yeah, that's a good question. I don't have the perfect answer for you now, but there's some indications for accretion flows that they might be enhanced in carbon relative to something less volatile like silicate. So that would lend to support this picture. There's other things that we can do to test this picture. So James Webb will test this picture. We'll potentially look at small CO ice grains. If we see lots of small CO ice grains, then this is not what's happening. A few other things. So we can also now get external measures of disk diffusivities. So the diffusivities, that's the main tunable knob in this modeling, and the answers that we get, so for some bulk alpha in the disk, are in the range that you would expect, which is really encouraging. And then for a few disks, we can actually start to look directly at alpha, and so far we're consistent with those, but there's other ways that we can be testing this and narrowing it down as well.
Sorry,
Yeah, I had a question. Sorry if I missed this, but what sets up the initial grain size distribution of dust grains? And are you saying that this ice formation is affecting that, or is it just affecting the position of that the grains?
Yeah, so in our modeling, we start with 0.1 micron size grains, like an average ISM size grain, and then we allow them to coagulate and grow and also form ice. So all of that happens self-consistently. You can imagine the initial size distribution being something more broad, where you have larger grains, and that actually enhances this effect. So you even quicker form ice on larger grains. And there's a lot of interesting implications. So you could also think about if different compositions, like if carbon grains and silicate grains have different initial size distributions, you might expect their later aerodynamic properties to be different because they form ice differently.
Charlie?
Are there other kinds of ice that would provide complementary pros of the structure of the disk?
Yeah, I think so. So you can definitely, well, so something like water ice, those features might be more readily approachable with James Webb. So looking at how they are spatially distributed throughout the disk, so that's modeling, that's really the obvious next step to do. Yeah, that'd be my short answer.
Okay, thanks, Diana. Let's have David set up next.
Okay.
Okay, so, yeah, David, please tell us about step size errors and Buddy.
Yeah, so this is work in collaboration with Richard Zeeb in Hawaii and Sam Haddon, who was a postdoc until recently here. Let me start with my conclusions. So despite several centuries of progress, the question of solar system stability remains unsolved. And I'm going to try to convince you that modern attempts to address this question are affected by numerical instability and chaos, which overpredicts the instability of the solar system. And I'll describe how we're currently attempting to address this question unhindered by numerical chaos effects. Let me give a brief history of the stability of the solar system, what we know about it. This kind of starts with Kepler and Kepler's first law. So he states that planets orbit on ellipses, and according to this picture, the solar system is perfectly regular. Several decades later, we have Newton, who comes along with his universal gravitation, so the planets interact with each other. So there's a possibility then that there's some instability. The planets can scatter or collide. And Newton himself believed the solar system stability was destroyed because of his gravitation. But he also thought that God intervened to make the solar system stable. So the picture was not clear. At the time, Newtonian gravity was still not on firm ground. Then we have to wait like a century later for next major development. So Newtonian gravity is, the differential equations are very hard to solve, but what Laplace and Lagrange looked at are how slowly varying orbital elements are changing. These are called the secular equations. And you can write these equations as a series in small parameters. And what they found is variations in the semi-major axes vanished to first order in masses. So this looks like a good sign for the solar system being stable. So there are a lot of other developments, but let's go to the present time. We're aided a lot by digital computers. So from 1988 to 2009, there are a lot of short-term studies of the solar system, both solving Newton's equations, those differential equations, and the secular equations. And here's Jacques Lascar, who has done a lot of work with the secular approximation. So in 2009, we really have the first realistic long-term solution of the solar system to address this issue of the stability of the solar system. And it's done by Lascar and Gastineau. They include a lot of interesting physics, so the Newtonian equations, of course, but also GR for Mercury, which helps to stabilize it. And also some effects of tides and the moon and massive asteroids. One thing they find is that there's an instability probability of about 1%. And the reason we talk about percentages, the solar system is a chaotic system, so we have to look at ensembles of initial conditions. So there's a possibility of collision with Venus or the Sun, for example, of Mercury. So that brings us to the present day, and I'm going to try to convince you that this work and several that have followed are affected by numerical instabilities. So just some basic maths we're on the same page. If we approximate the solar system as a conservative system, we can write down the Hamiltonian. The dominant part is this A function, which is Keplerian motion of the planets. And I've just chosen some canonical coordinate system. And then there's the remaining Hamiltonian, including the interactions between the planets. The basic way to solve this, which is pioneered by Wisdom and Holman, is to just form operators out of these two functions, just like we do in quantum mechanics, and produce time evolution operators, and that's shown down here. So we have what the Wisdom-Holman method consists of is alternating these operators. So we do time evolution operator for B with a slightly different 1/2 coefficient than A and then B. And it turns out this gives us an approximation to the solar system trajectories as a function of time. So this is our solution to the trajectory of the planets. This is what Laskar and Gastineau used, and basically what every modern author uses, or some variation of this. And it's very powerful because this is also symplectic. So that means that such a method respects the symmetries of Hamiltonian dynamics. Phase space volume and other higher dimensional volumes are conserved. Okay, so the one problem here is with this method is, well, it's not a problem, it's a feature, is that we have to introduce this artificial parameter, which is a time step. So what happens with an artificial parameter? This can have resonances with real time scales, such as Mercury's period. And resonances, so these resonances can lead to chaos in artificial trajectories. And this was first noted by Wisdom and Holman, surprisingly not studied very much at all since then, just in a few papers. So let me give you a few examples of what this looks like, what this means. Let's look at possibly the simplest chaotic problem, the restricted three-body problem. We have a star, and let's call this Jupiter, in circular orbit, planar problem, and 2D problem. And this is the rotating frame. So we have a test particle with 2 degrees of freedom. So let's explore the motion, the possible motion phase space available to this particle. And the way we can do that is with surfaces of section. So let's focus on this left panel. The way this works is we can plot the phase at conjunction between test particle and Jupiter, and on the y-axis is some proxy for the semi-major axis. Specifically, what I plotted is the first order mean motion resonance between test particle and planet. So this number indicates which resonance that is. So the important thing is we have this. This indicates the chaotic C, where the test particle executes chaotic motion, and there are these regular regions. So these are initial conditions for which the motion is regular periodic. So this is the resolved case. Now, in the unresolved case, this is the case where we have step-size chaos. Now, why do I say resolved? The important thing, it turns out, is to actually resolve your pericenter. So you want to look at, so this is a function of eccentricity. So the higher the eccentricity, the smaller the time steps you need to take. And actually, I'm just looking at simple planetary systems here, but this issue applies much more broadly to all kinds of dynamical problems that involve the n-body problem. But let's focus on this simple planetary problem. When the pericenter is unresolved, we can see the phase space changes significantly. This chaotic C, the area grows significantly. Some of these invariant curves are destroyed. So this is what we mean by, this is one way to look at what this numerical chaos is doing. And this also affects the possible stabilities. Okay, so what we did is we looked at several recent studies of the solar system, including Laskar and Gastineau and some other authors, and we quantified how much they're subject to this step size instability. All of them are subject to step size chaos. it turns out they don't need to be. You can set this problem up in such a way to avoid this, but all of them are to some degree. And another issue that comes up is orbital elements like the eccentricity diffuse in time. And because the diffusion's related to the chaos quantified by the Lyapunov time, that's also affected. So let's see what that looks like. On the left here, I plot the eccentricity of Mercury every 250 megayears, and this is a PDF. So the eccentricity is diffusing with time. And again, as I said before, because it's a chaotic problem, we're looking at ensembles of initial conditions. So that's how we can write a PDF or draw a PDF. We can fit Rice functions to this. This is a 2-parameter family, one variable for the centering and one for the width. And what we did is we compared, the first thing we did is we compared this blue curve so we can fit Rice functions to these 2 authors, these 2 data sets as a function of time, and look how the eccentricity is diffusing differently among different works. This blue is the one that was more affected by step-size chaos, and this black was less affected. And the idea is that they differ statistically. There's a significant difference statistically between the two in the shapes of what the eccentricity is doing. And this also extends to the instability. So this was observed by Abbott et al., who weren't even worried about step-size resonances, but it turns out their work supports our conclusions. They were just interested in the instability probability as a function of time of the solar system, and they looked at these different data sets, and they found that this one, which is the most affected by numerical instability, has more instability probability, especially at later times. Better numerical integration should potentially change this, maybe significantly, and that's what we're working on right now. So that's kind of the future work in collaboration with Sam Haddon and some others. What's Mercury's true instability probability, and how does that affect the chaotic nature of the solar system? And I don't know how I'm doing on time, but here are my conclusions again. So I hope I've convinced you. Well, there's been a lot of work on the question of solar system stability, but it still remains unsolved. And modern attempts have really made progress on solving the equations, but they're still affected by numerical instabilities. And the important thing is to try to eliminate such instabilities. Yeah, thanks for your time.
Questions? Anyone but Charlie? Students are allowed to ask questions too, and encourage.
Are you saying that you found a way to model and reduce the numerical chaos?
Yes, that's right. So the important thing is to resolve pericenter. So if you could set something up that resolves all your pericenters, so Mercury's eccentricity can grow, but if you're always able to resolve its pericenter, you can avoid this, and that's what we're currently doing, choosing time steps that do this. And this actually applies to any kind of n-body simulation. So it's a broad problem.
I didn't mean to cut you off, Charlie.
That's fine. Can I have a question then?
Yeah.
So I mean, in other fields, I know people do these convergence tests. So have those not been done here, or were they done but you had to get so far down in terms of decreasing that h parameter that people hadn't seen this effect? Like, why? It seems like you just change h and you see how things change. So why?
Yeah, well, the problem is these are very expensive computations, first of all. They take months, right, to run the solar system for billions of years. So it's not that simple to just change a parameter. And we're looking at things that are very rare. Oops. Rare events like instability probability. That's very rare. You can't just do a convergence test on your instability. And similarly, for the diffusion in the eccentricity, it's a process that happens very slowly. So it's not easy to do a controlled experiment on these kinds of things, I'd say.
could you say a little more about what an ensemble of initial conditions looks?
Oh, sure. Yeah. It's a good question. So for any chaotic system, you just need to perturb the initial conditions a little bit. So I can choose to perturb, let's say, Earth's position by 1 meter, and that's good enough. Or I could choose to yeah, there's some small difference.
How many different instances
Oh.
of an ensemble?
Yeah, so for these different data sets, I think this one had a few thousand. Yeah, Lasker and Gastineau, over 1,000, I think, too. That's what people are able to do. I don't remember the exact numbers.
And then when you show the probability of instability, you're just saying what fraction of those cases.
That's right. Yeah, and
So if you're getting 10 to the minus 3 probabilities, you must be running many thousands of tests.
right. And they're clever. So actually, the point of Abbott et al. Was to create a mathematical trick to be able to get these a mathematical trick to get these instability probabilities without having to run so many. So I mean, I don't remember the details, but basically, if something might become unstable, you focus on those trajectories and do more of those. And yeah, so there's some clever things you can do.
I see. Check in after a few gig years and see how it's coming.
Right.
Then you know which one's the part. I think there's one more question while Raul sets up. Was there another question? Well, if not, let's thank David again. Okay, so yes, welcome Raul, who is officially an ITC fellow.
Okay. Should I start? Okay. So thank you. I'm an ITC fellow, and today I'll talk about reionization and specifically looking at line intensity mapping during the epoch of reionization. So I'll just briefly explain what line intensity mapping is. It's kind of like the CMB map. So instead of looking at individual galaxies on the left here, you just see some plot of individual galaxies. The dots are galaxies here. You take a low resolution map of the emission lines arising from these galaxies or from any of the gas in these galaxies. So you can have emission lines from star forming regions, or you can have emission lines like 21 centimeter, which tells you where the neutral gas is. And then you create this kind of map, and these fluctuations in this kind of a low resolution map will tell you something about the large scale structure of the universe, because that will tell you how the galaxies are distributed and how the gas in the universe is distributed as well. So this is a very powerful technique because you do not need very high resolution to do this. You can use low resolution telescopes to detect a variety of lines and to understand both astrophysics and cosmological processes. So why is line intensity mapping powerful in the epoch of reionization? Well, so 21 centimeter, you can do 21 centimeter intensity mapping, and that's what telescopes like Hera and SKA are Hera is currently doing it, SKA plans to do it. So basically the distribution of the neutral gas during the reionization process will be measured by 21 centimeter intensity mapping experiments. And then if you look at emission lines from galaxies themselves, like CO, will tell you something about how the molecular gas is distributed. C2, O2, O3, H alpha, H beta, all these lines are related to the star formation in the galaxy, so that will tell you something about how the what star formation is taking place in these early galaxies. And if you can combine both the emission lines from the galaxies and the emission line from this neutral gas, you basically get a complete picture, because you can track the reionization process and track the sources that are galaxies that are responsible for the reionization process. So it's a very powerful technique to understand reionization. And so that's why there have been a lot of experiments which are currently doing intensity mapping or about to come online. So a variety of experiments looking at 21 centimeter emission for neutral hydrogen, looking at CO and C2, so molecular gas and partially ionized gas, and mainly rest frame optical lines here, like O2, O3, Lyman alpha, H alpha, and H beta. So you can see there are a lot of instruments which are currently running or about to come online. And you need to make predictions for what these instruments will see. So in order to make predictions, you need a few ingredients. So you need accurate reionization history and topology. You need to understand how the reionization process is taking place. You need an accurate galaxy formation model because all these lines are very sensitive to your star formation rates, metallicities, and dust content in galaxies. You need to have accurate radiation hydrodynamics because radiation plays the most important role in all these processes that I mentioned before. And you need to model these emission lines properly as well. And finally, you need a very high dynamic range because the lines like H alpha and H beta arise around young stars on parsec scales, whereas reionization happens on the universe scale, so about gigaparsec scale. So you need a very high dynamic range in order to get all of this right. So what is the current state of the art in this to understand line intensity mapping? So usually it's not that evolved, I will say, this topic. So what people generally do is they paint on luminosities onto some halo masses. So they take a pure dark matter only simulation. They assume some properties of galaxies, and they assume that there is some kind of emission line arising from this galaxy. So this is the function that they take, and they paint this onto a dark matter simulation, and they arrive with this H alpha line intensity map on the right here. And the 21 centimeter map is also quite not well modeled because they kind of use like excursion set formalism. So that's why you get these exactly spherical bubbles, which you do not really see in if you look at realistic simulations. So this is the current state of the art. So the question is, can we improve it? And that's where the Thiessen project comes in. So we basically have fully consistent, large volume, high resolution radiation hydrodynamic simulations. And we put out 4 papers recently on this topic. And in this, you can see the power of these reionization simulations. So the background is the evolution of density and temperature of the gas. And you can see how this ionization topology varies or evolves from low redshift to high redshift. And you can even go back and resolve individual properties of dust, gas, temperature, ionization state, and photon density, and even resolve individual galaxies. So here, as an example, I show mock JWST and ALMA image of one of the more massive galaxies in the simulation. And it's also great, as I said before, because here I plot as a function of the box size of the simulation, the minimum cell sizes achieved at redshift 5.5. Most of the simulations either have very high resolution, and the penalty is a low box size, or a very large box size, and the penalty is a very low resolution, whereas Thiessen here is at the bottom. And you get both. And so that's the power of these simulations here. So these simulations reproduce accurate reionization history. On the left, I show a neutral fraction evolution as a function of redshift with the black points are the observations. And you can see we follow that line. It also reproduces the correct mean free path evolution. Previously, without these high resolution simulations, people thought that the mean free path evolution was quite shallow. But we show that it is quite steep. And these observational points came after we put this line here. So the new observations kind of tell us that our model is correct here. And in addition to the large-scale reionization history, we also get the galaxy properties right. So on the left is the stellar mass-halo mass relation, and the blue is the expected value from abundance matching relations, and the black is the Thiessen simulations, whereas other simulations which try to do this are either forming too many stars or too few stars here. And on the right here, I show the gas metallicity mass stellar mass relation, and the shaded region and the lines are the simulation, and the the black points are the observations. This is just to show you that we get a lot of things right. So now, how can we? So using the simulation, which gets a lot of things right, we want to model the emission lines. So the emission lines are pretty hard to model, as I said. So most of these emission lines arise from regions around newly forming young stars. So most of them arise from highly ionized H2 regions. Some arise from partially ionized photodissociation regions, and the others from GMC and atomic gas. So now that we know that we have the right stellar ages, star formation rates, and metallicities, we can model emission lines from the galaxies in the Thiessen simulation. So we paint H2 regions onto these galaxies, so that we take self-consistently the star formation rate, stellar ages, metallicities, and the dust content. And we use a Monte Carlo post-processing code SCRT to understand the effect of dust attenuation in these galaxies as well. As you can see, an example of a JWST mock image of 2 galaxies, and also emission line maps of the galaxies in our simulation. So this process basically gives you the full SED of the galaxies in a simulation of all the galaxies, and then you can calculate what the emission lines are telling us. And I basically look at a lot of emission lines in both the RESPEM optical and the IR. I want to concentrate on two lines here. So let's first look at H alpha. So at redshift 0, the H alpha relation is given by this red line here, modeled by Koenig at 98. But if you look at what the H alpha luminosities tell us in this simulation, we are slightly above at low star formation rates or low metallicities, and the dust attenuation makes it lower at high star formation rates. And the reason we have higher than expected H alpha luminosities is because these low star forming galaxies are less metal enriched, which means that the stars themselves input more Lyman continuum radiation, which increases your Lyman H alpha emission. You can also look at metal emission line like O3, which we are below the observed relation, and the observed relation is in blue. And it's the same reason. You have less metals, so you have less emission from the metals themselves. So the point I want to make here is you cannot use redshift 0 scaling relations in order to understand line intensity mapping maps. And in fact, these changes, these small changes that you see on this plot, and because it's a log plot, changes your mean intensity by a factor of 3 to 4. So these small changes are very important in order to understand line intensity mapping. And as I said, we have full radiation hydrodynamic simulations, so we can get both the 21 centimeter emission, basically from the neutral gas, which is at the top, and H alpha emission, which is tracing the galaxies at the bottom. So we can trace the reionization process and the sources responsible for the reionization process together. And then we can look at how these maps correlate using the cross-correlation function. So here, I plot the cross-correlation function between 21 centimeter line and the H alpha line as a function of wave number. And this is a model of reionization in which only large galaxies dominate your reionization process. So this solid line is negative correlation, dashed line is positive correlation. And you can see that there is a wave number in which this transition goes from negative to positive. If you have a reionization model where only small galaxies contribute to reionization, your transition wave number shifts. And you can also do this with an alternative dark matter model, and your transition wave number shifts with your underlying dark matter model as well. So the point is you can use the transition wave number for a whole bunch of different lines to understand or to place constraints on what galaxies contributed to your reionization, and also to understand what is the underlying dark matter or dark energy model. So this is a very powerful tool to constrain both astrophysics and cosmology during using reionization epoch of observables. So to conclude, I'll say, Thiessen is a very large volume simulation which can make predictions for a lot of observables, and using accurate line intensity mapping measurements for 21 centimeter and nebular emission lines, it has the potential to place constraints on both astrophysics and cosmology using this new technique. So I'll just leave you with a movie of this simulation. Thank you.
That was perfect timing. Let's start back there.
Sure. So are you using clouding in order to generate these emission lines?
Yes.
Could you talk a little bit about how that's
How
how are you using? You said there's a cloudy grid.
Yes.
Emission lines. Could you just talk a little bit about how, like, a little bit more about how that's done? Not how to use cloudy. but-
Yeah, so the ionization parameter is set to constant, but the metallicity and the age of the stars is an input parameter for the cloudy models. And then that gives you emission lines from these, you assume some stellar population synthesis model, you assume some ionization parameter, and then the metallicity is given by the stars themselves, and the age of the star is also given by the simulation. Yes, each star has its own H2 region around it, and that's how you do it. Yeah.
I guess a quick follow-up, sorry.
Sure.
So your resolution is quite fine, so I was wondering what happens if two stars have an overlapping ionization
Right.
region?
Well,
How that cross effect is.
yeah, that's not modeled here. We are currently running even higher resolution simulations with a better ISM model, and we are doing it self-consistently without using cloudy. I can talk to you about that later if you want. Yeah.
Sarah, did you have a question?
Thanks for the great presentation. I was wondering about the K transition that you showed. Is there any observation that's proposed or planned that can reach that resolution?
Yeah. So I mean, this is a very powerful technique, but we are still in the very initial stages of both 21 centimeter and nebular emission intensity mapping. But at some point we will reach enough this one to do it. So Sphere X, for example, will look at all these lines. It will be launched in 2024. Hera has currently upper limits of 21 centimeter. Probably we'll get something in 3-4 years. So that time scale is what we are looking at.
And is there any black hole setting model in your simulation?
Sorry?
Is your simulation considering the effect of AGIs and the
Yes, there are black holes in the model, but in this model, the black hole contribution is less than 1%. So, yeah.
I have a question on the cross correlation plot too.
Yes.
The amplitude also seems to change a lot from model to model.
No. I changed the amplitude because otherwise it will overlap with each other.
Okay, because I was expecting this model
Yeah.
to be lower.
No. If I plot one on top of each other, you won't see anything. So that's why I changed the amplitude.
Okay.
Yeah.
Okay, any other questions? George?
This is really great. I had two short questions. One was I totally missed what PSIM stands for.
Oh,
And the other one was, what is the minimum size survey you think that should be done at sort of redshift of, let's say, 6, right? That would cover enough volume for you to be able to tell the difference between those K numbers that we're talking about. It looked like it was about half a megaparsec per moving, something like that.
yeah.
By kind of fast, but
Yeah. Well, okay. So first thing, Thyssen, it's not an acronym. It's an Etruscan goddess of dawn, which seemed appropriate. Second, it's about sensitivity limits here. So 21 centimeter, for example, does not have too much sensitivity below 1 or so. It kind of goes up quite high. And the nebular intensity mapping measurements, I'm not sure. I haven't looked at what sensitivity limits there are. So I don't have the answer for this. So this is kind of a purely theory kind of thing where you can do things. But yeah, I hope to have students working on trying to figure out what the telescopes or how you can differentiate between these models. It's encouraging that you can differentiate, but the question is how properly you can do it. Yeah, that I haven't done that work yet. Yeah.
Okay, let's thank Rahul again. Feel free to grab an extra sandwich on the way out to make a good midnight snack.